This is with Stefan in the jury, and so this is one of the reasons why I'm here today, to try and discuss some of the stuff that we didn't understand from the PhD thesis. And what you see is a weird way of making sprays that I will explain to you in a second. You know, or some of you at least know more about sprays than I do, but I've always considered it very complicated, so I stole this picture from Emmanuel Villarmeau, who has a liquid jet, a large liquid jet with air co-flowing, which is one of the standard ways of making a spray. And then you see these long wavelength perturbations on the jet that might be a Kelvin-Helmholtz instability. And then you have these ligaments forming because of gravity, which I call the lava lamp effect. And this is a Rayleigh-Taylor instability. And once you've formed these liquid threads, you will have the Rayleigh plateau instability that finally leads to droplets. Yeah, but so to understand what a droplet size distribution from such a spray would look like, you would need to understand at least 3 instabilities in all gory detail. Yeah, and still it's very important because, as I mentioned, spraying is probably most used in agriculture. And you see here what happens if you do agricultural spraying. Basically, you don't want too large droplets if you spray, because the large droplets will bounce off the water-repellent plant leaves. However, if you make small droplets, and that's what you see here, they will not end up where you want them, namely on the plant leaves, because you can imagine in all these 3 situations, if there's the slightest gust of wind, the small droplets will drift away. This is called spray drift. And will end up there where you don't want them. Yeah, and so this is especially a big problem in the Netherlands, where there's a ditch with water around every agricultural field, and so these droplets drift into the surface water, and the surface water ends up being our drinking water. Yeah, and so this is a movie of how agricultural spraying is done. This is now a sheet. My first picture was a cone. You can see a sort of flapping flag instability that leads to the formation of these ligaments, and these ligaments are polydispersed, and so they break up into a drop size distribution that is really very wide. Yeah? So optimal for spraying onto plants would be 200 micrometers. But then there's lots of large droplets which will bounce off and end up on the ground and then go into the groundwater. But the most important part for pollution are the small droplets. In agriculture, one says all droplets smaller than 100 micrometers will be prone to drift away. And so that constitutes almost 20% of the spray volume here. Yeah, and that's a lot of very dangerous pesticides. What we were trying to do was not agricultural spraying. I actually already gave a talk about how to solve this agricultural spraying problem for D'Alembert a couple of years ago. So I won't talk about that today. What I want to focus on is trying to make better medical sprays. And so the problem is roughly the same here. So this is your typical nose spray, filmed with a rapid camera, of course. And so this also makes a sheet. It's very beautiful, but it's extremely messy. Yeah, and so this is your typical nose. This is actually a transparent nose model. And so what you see is the droplets are polydispersed and very large, meaning that they end up only in the front of your nose. And that's not what you want, because most medications, most drugs, you would want either homogeneously distributed over the nasal cavity or in a specific region. Yeah, so the region here is actually your olfactory region, and so if you have olfactory problems, there's actually drugs you could deliver to that region that would help you to smell again. Because this was part of a proposal for the EU, there's the stunning figure that all of us together spend $45 billion every year on nasal sprays, which is really bizarre. And so the easy solution to all this messy drop generation problem seems to be to, instead of making liquid sheets that do complicated things, just make a jet. Yeah, because the Rayleigh instability tells you that if you can make a nice jet, you will get droplets that are 2.4 times the size of the jet. And so this is actually a very fine jet, which is part of my talk that I will explain to you in a second. But if you can control the hole size very precisely, you can control the jet size, and so you can control the drop size, and you can do magical things in drug delivery. Yeah, so if you know what your target area is, you actually exactly know what size droplets to make. So bigger droplets remain stuck in your nose if you take a nose spray. Intermediate droplets, like 10 microns, get stuck in your throat, and so that's now used, for instance, for throat anesthesia for intubations. And even smaller droplets, like 4 to 8 micrometers, go into your lungs. So think about asthma medication, for instance. And smaller than 4 micrometers, you actually breathe out again, so that you don't want. Yeah, but so if you can make droplets of a well-defined size, you can do targeted drug delivery, and you need this because you don't want your throat anesthetic to paralyze your lungs, for instance, right? And so this is where we started working on what we call Rayleigh sprays, which are sprays made of a collection of these small jets. And so this is just false color to be pretty. But you can see that we can make a spray of very small droplets. And that is really what is so special here. It's much better on my screen than on this screen, sorry. Because we have what we call nanotech nozzles. Yeah, and so the nanotech nozzles are made from a tiny little piece of silicon wafer with a hole in it, and over that hole one can put a silicon nitride membrane, and now one can use all the tools of semiconductor manufacturing, nanolithography, to make very precise holes of a very well-defined size into this membrane, right? And then the membrane goes into a setup that will eventually lead to your nose spray, if you want to think about nose sprays. Yeah, but we can make basically holes very precise, any number we want, between 1 and a couple of hundred, any size we want, between 2 micrometers and 128 micrometers. Yeah, so this is a new tool that is really nice. And then we start out looking at a single jet. We have a fast camera, we have a backlight, and then we can do another neat trick. which is, if you know what the Rayleigh frequency is, you can try and excite the nozzle at the Rayleigh frequency, which we do here with the transducer. And if we do, we get an extremely nice monodispersed droplet train without any satellite droplets. Yeah? So here you see a very nice droplet train, perfectly monodispersed droplets of the size that we decide they should be by choosing the size of the nozzle. Here you see that it's a bit more messy because you can see, at least if you're in the front row, that there are little satellite droplets that come from the breakup process. There's lots of interesting stuff going on here. You see here you have a jet that then eventually breaks up into droplets. If we excite it, the jet actually becomes smaller, which is something we would like to understand. And the bad news is that we can make perfectly monodispersed droplets, but then unfortunately further from the nozzle the droplets do coalesce, and that will make that the drop size distribution again becomes broader. And so that's what I want to do today, and then eventually I'll get back to trying to make a nose spray that works better than the one I showed you. Yeah, and so let's first ask a naive question. What gives the breakup length of the jet? D'Alembert, can I have your votes, please? Surface tension, yes? But how do I go from surface tension to a jet length in centimeters, millimeters? Well, we all learned at Hydrodynamics 101 that there's the Rayleigh instability that does this, surface tension. And so there's an initial perturbation that grows until that grows exponentially until it reaches the size of the jet, and then by definition a drop is formed. Yeah, and so in theory, the Rayleigh theory says there's an exponential growth with some growth rate, yeah, the inverse of the or the same thing as the frequency with which I moved my piezo, but I need some initial perturbation that should grow until the thing breaks up. Yeah, and if you say that the jet length is the same thing as time, yeah, because you have a constant velocity of the jet, you know if the growth has attained the diameter of the jet, that your jet will have broken up. Yeah, and so from the time necessary for growth and the velocity of the jet, you immediately get the breakup length of the jet, which non-dimensionalized by its diameter goes as square root Weber times some logarithmic factor where there's the initial perturbation that has to grow. And then the only question is, what is the initial perturbation? Well, we looked in the literature, and it says the actual perturbation which disrupts the jet comes from building vibrations, sound waves, and from you walking around the laboratory, which is not very satisfying. Background noise in a laboratory, pumps and compressors may be present at amplitude sufficient to cause instability, etc., etc., etc. Yeah, and so the real answer is we don't know. And so we had a number of hypotheses. Environmental noise, you probably would have thought about nozzle imperfections. There's actually an interesting theory that the noise from the breakup itself travels back to the orifice and causes the eventual breakup. And then there was this crazy idea that the surfaces are always rough because of thermal fluctuations, and that could constitute the initial perturbation. Yeah, and so we worked, we being Stefan, of course, and we did lots of different nozzles. So we did simple tubes, we did rough tubes, we did reservoirs. I bought a whole set of very expensive nozzles. Yes?
But at this stage, you can estimate the size of the perturbation that will give you a certain breakup length.
That's exactly what I'm going to do. But not before torturing you with a couple of experiments that we did. I bought a very expensive set of German nozzles called smooth jet nozzles, and so it has a tapered entrance that would really lead to smooth jets. We made a flow rectifier from YouTube that actually does give very nice and stable jets. We have our microjets from the nanolithography nozzles. And so we did 1 million experiments and we concluded there's no difference between the different jets. Yeah, so rough nozzles give the exact same jet length as smooth nozzles, provided the diameter is the same. Okay, then it must be environmental noise, right? So we put the whole spray setup in a vacuum chamber, so no air currents. The vacuum chamber was on a vibration-free table. And so we went through all this trouble and we didn't see any difference. As Trump would say, very sad. Then there was this idea that the drop breaking up here would cause some perturbation that might travel back to the orifice and then create the breakup. We think this is actually a thing, but only very close to the dripping to jetting transition. Yeah, so this is something we're trying to do with Basilisk today as we speak. But for our jets, actually they're so fast, especially the microjets, that there's no mechanism that would allow things to travel back at 10 meters per second, which is the speed with which these jets come out of the nozzle, to cause a breakup. Yeah, and there's a very simple experiment that you can do. This is a movie, but you don't see anything happening. You see a bit of fluctuations here. But what we're doing is we're spraying into a reservoir, or we're jetting into a reservoir, and then we're withdrawing, or we're retracting the nozzle from the reservoir. Yeah, and so if it were noise from the breakup itself, we've suppressed the breakup itself by jetting into a reservoir, then we would be able to make a much longer jet. And we don't. And so the only thing we were left with, or our only hypothesis that we were left with, was thermal capillary waves. And so we tracked the instability. Yeah, you can look at how the instability grows with the distance from the orifice, just by looking at different distances from the orifice. And then we can do something very weird, is we take all our data and then we extrapolate back to where the initial perturbation should have begun. Yeah, and then we find a length scale, if you believe this extrapolation, that is molecular, an angstrom, a molecule. Another way of doing it is if we use our droplet train with the piezo, we can slowly decrease the amplitude of the piezo to go from a perturbed system and a nice droplet train to an unperturbed system, and then again extrapolate. Yeah, and so this is again plotted in this logarithmic ratio of the jet diameter to the initial perturbation. And again, here we find something that is only compatible with a molecular scale. Yeah, and so, as Stefan said, I worked with Jacques Meunier at the École Normale Supérieure for an odd 20 years, and Jacques Meunier is the inventor of the capillary waves. And so if you look at a very small scale at a liquid-vapor interface, it looks like this. Yeah, so these are just Lennard-Jones molecules bouncing around because they're warm. And this is not smooth at all. This has a certain roughness. Yeah, and Jacques Meunier derived the capillary wave theory, and using equipartition, you can write down an expression for the root mean square amplitude of these thermal fluctuations as a function of the thermal energy and the surface tension. Yeah, so if you plug that into the Rayleigh prediction, saying that this is the amplitude of the initial perturbation, you get an expression, an explicit expression as a function of kT, the surface tension, and the diameter of the initial perturbation. And so then we being again Stefan, measured 100 jets, and then we measured another 100 and another 100, and then we put all the data together. And so these are all our different jet setups with different liquids. We didn't do many different temperatures because it's complicated. But they all lie very nicely on the straight line predicted by capillary wave theory. Yeah, so this is a very nice data point, which is from an old simulation by Mosler and Landmann, who actually did an MD simulation of nanojets. And they claimed nanojets are different from regular jets, because for nanojets you can actually see the fluctuations, and you can see that the fluctuations lead to the breakup of the jet. And we're now saying, well, it's on our line, and so also for all the other jets it's the fluctuations, only you cannot see. Yeah, and so the weird conclusion is that every time from today on that you will look at the dripping faucet, at a tap that makes droplets, you will have to realize that it's thermal fluctuations that are 7 orders of magnitude smaller than the droplets that you're seeing that actually cause this breakup. That's nice, right? So we published Rayleigh's theory in PRL a couple of months ago. Yeah, the only thing is we explained that it was actually thermal fluctuations. Okay, that solves that problem. Second question is then, what gives the drop size distribution? Yeah, and so here again you see this nice droplet train, but then as we go further and further from the setup, from the nozzle, we actually get a more and more messy distribution. And so normally the gospel for spray formation is that it's all random processes. Yeah, and so all this complicated stuff you could think of as, I have a line, yeah, which is a ligament of water that I cut in random pieces, and then I cut it again in random pieces, and I cut it again in random pieces, and then in the end I will end up with a size distribution that is due to the sum of all these random processes. Yeah, one of the nice things about this argument is that you can also do it the other way around. If you do coalescence, you start out with, for instance, a train of very monodispersed droplets, and you randomly connect them together. You would also end up with such a random distribution. Yeah, so coalescence and fragmentation are the same process, but only the other way around. Yeah, and that, according to some eminent scientists, leads to a universal distribution of both fragmentation and coalescence. Yeah, and so typically, so this is again the agricultural sprays, what you get is a gamma distribution, and sometimes it's a complicated gamma distribution. If you want to know more, you should read the collected works of Emmanuel Villarmot, because he's the great advocate of these gamma distributions. Yeah, and they seem to describe at least the agricultural sprays very well. However, this supposes randomness, and so if you look at these coalescence processes, this is all but random because they have to have a velocity difference, but then once they've coalesced, they will have the same velocity. Yeah, and so this is clearly correlated motion, which basically breaks the assumption that everything is random. Yeah, and it's a very nice academic case, because it turns out that if we carefully measure the velocities of the individual droplets in the droplet train, we get a Gaussian velocity distribution. Yeah, and it's this distribution that will determine whether things will coalesce further on or not. Yeah, if they don't have the same velocity, one will catch up with the other and they will coalesce. Yeah, and so we again did lots and lots of experiments. Yeah, and then you get at different distances from the nozzle, you get a different size distribution of your drops. There's one small experimental caveat. What you want is the radius or the volume of the droplet, and so if the droplets have inertial oscillations, you actually have to do some image analysis and actually determine the volume of the droplet while it oscillates. Yeah, and so if it's not completely circular, you have to correct for that. But that we can do, at least the computer can do. And then we get a drop size distribution that looks like this, which is weird. This is very close to the nozzle, and you see actually the initial droplet size, and then you see some higher harmonics. Yeah, but if you go further, much further downstream, this of course smoothes out, and then you get this. Yeah, so what do we do now? We can try and fit it to a gamma distribution that doesn't work. And then there was a very clever theoretician who worked with us for a couple of months, Aritro Mukherjee. I should have mentioned him on the authors, who actually found this old paper about planet formation. Yeah, ballistic aggregation happens in space all the time. There's stuff that encounters each other. This clumps together, and this eventually leads to the formation of lovely planets like ours. Yeah, and so this is a ballistic aggregation problem. In space it's complicated, but here we have a very nice one-dimensional problem with objects that move with an average velocity that are all roughly the same size, and they have a Gaussian velocity distribution. And it turns out that this is exactly what Mr. Frackenburg in the last millennium solved. And so there's 3 predictions. One is that the average mass of the object should scale as time to the 2/3, so the distance from the orifice to the 2/3. That the size distributions are self-similar, meaning that they don't become any broader when we go further from the nozzle. And there's actually an explicit prediction for what this size distribution should look like. And so if we rescale the droplet diameter by the maximum, it turns out that they are self-similar. If we see how the maximum or the average changes over time, we do find this 2/3 law. And then if we fit the drop size distribution to the prediction, we actually find that it fits really, really well. Yeah, and this looks a bit different from the distributions before, because this is actually the diameter and this is the mass distribution. Yeah, so this is the diameter to the power 3. Interestingly, the gamma distribution does not fit our data. Yeah, and so we think that means that we actually found the signature of this randomness of these drop size distributions. Yeah, so we have a distribution of drop sizes in a much better controlled system than any other experiment, I would say, that shows that correlations are in fact important. Yeah, the question is then, why do all the other distributions look like gamma distribution? And that's something I'm discussing with Stefan. He will tell me after the talk what the reason is. Okay, so I've been playing around with jets, but what we wanted to do is make sprays. Yeah, and so if we just use a number of nozzles, we can get a nice spray cloud, and this is the way that we do it, and we look at it again. And now we can do the physics of sprays. And so this video is again much nicer on my screen than here, but it's still pretty nice. That's a spray. And this is what we call a puff, where at some point we just stop the spraying and see how the puff moves through space. Yeah, and the reason why we were very interested in the puff is, of course, the fact that you puff, you sneeze when you have viruses. This was in the corona period, and so if you look carefully, you can see a face here, and this is actually a picture made by Lydia Boruiba of a puff caused by somebody's sneeze that travels through space, and you would actually like to understand how far that travels in order to be able to keep your distance, right? And so there are two predictions, also from Lydia. If you keep on pushing the spray, it should advance like the square root of time. But the puff actually slows down because you're no longer pushing it from behind, and then you should get t to the power 1/4. And so from the two movies I showed you, we get a very nice, I think, yes, we get a very nice 1/2 for the front of the spray propagation. And then for the puff, we actually see 1/2 while we are still pushing the spray, and then it crosses over to 1/4 when we stop pushing. Yeah, so these are very clean experiments that show this nice crossover. We can do this with different number of jets and size of the jets. So these are 24 jets of 4 micrometer, very nice 1/2, and these are 120 jets of 4 micrometer, same thing. Yeah, and so we can make a spray as dense as we want because we can control very precisely the number of holes, the flow rate, etc. And so one way to think of this square root of t behavior is the fact that you see that there's a constant cone angle, and then by mass conservation you simply get that the front should propagate as square root of t if your volume flux is conserved. However, that doesn't explain why my jet remained a jet and this spray actually all of a sudden spontaneously forms a cone. Right? And the answer is, of course, Dalamer, can I have your votes again? No? Air friction, I think. Yeah, so we all know Kelvin-Helmholtz from the clouds, and so these are two different fluids, one charged with droplets and the other not, that move at different speeds, and that gives the Kelvin-Helmholtz instability. And so there's no reason why this shouldn't happen for our sprays. Yeah, and so Kelvin-Helmholtz directly actually predicts the constant cone angle. Yeah, so we were hoping that this would explain why there is a cone. And so if we do PIV, and again for you it's more difficult to see than for me, but you do see these recirculations. So this is the vorticity, the intensity of the vorticity, and you can see that there's a well-defined wavelength where the vorticity is large, and so this already looks a bit like the Kelvin-Helmholtz instability. But the proof of the pudding is in the eating. If we say it's air friction, we should remove the air and see what happens. Yeah, and so we were able to spray in a vacuum chamber. And so if we do that at a low pressure, it's very hard to see, but if you look carefully, you see just a collection of jets. There's nothing happening. And if we have a somewhat higher pressure, you can see, at least if you're sitting in the front row, that the spray fans out again. This is perhaps clearer. This is atmospheric pressure, and this is 1/10 of atmospheric pressure. And so you see that the fanning out completely disappeared. Yeah, so we can quantify this. So this is the spray cone angle. So the angle simply goes to something close to 0 at the finite air pressure. And this is the distance after which you actually see the cone, because you have some time, you need some time to develop the instability also. But the more interesting question was, of course, what gives the pressure for having a spray or just having a collection of jets. Yeah, and so we did a lot of experiments where we had an easy criterion for distinguishing between just jets and a cone fanning out. And so we could delineate the boundary, and then you can compare to the Kelvin-Helmholtz instability. And the Kelvin-Helmholtz instability says you have to have a critical velocity difference between the two media that is given by this. And before you can get the Kelvin-Helmholtz instability. Yeah, and so we simply plot this as a function of this, and then we get straight lines for two different nozzles, meaning different densities. The wave vector we get from the vorticity plot, it's roughly a centimeter or two. And then the only adjustable parameter, or what you get from the slope of this plot, is actually the surface tension. And so this is another discussion I was having with Stefan and Stefan. What gives the surface tension of a spray cloud, or what gives the surface tension of a cloud? Yeah, in the normal way of demonstrating the Kelvin-Helmholtz instability is actually the beautiful picture from the clouds that I show you. But a cloud doesn't have a surface tension. It might have an effective density difference. Yeah, so this is all small scale. So it's probably surface tension. Clouds are large scale, so it's maybe the density difference limit. But still, we have to find a way to actually explain this value of the surface tension that is roughly 100 times smaller than the surface tension of water. Yeah, and naively this makes sense because it's roughly 100 times less dense than water, the spray. But I would actually like to be able to say something about this. So that's one thing we don't understand. There's actually something much more important that we don't understand and that I want to finish on if I still have 5 minutes. Yeah? Which is this. So this is our spray nozzle, and there's an electrode here if you look carefully. And so the spray nozzle is grounded, and then the other end of this little lamp is grounded. And so apparently there's enough electrons in the spray to light this light bulb. That's what you're seeing here. I'll let that sink in for a sec because it blew our minds too. And so we all know about static electricity. Yeah, if you walk on a floor that is plastic and you turn, you try and turn the door handle, you can have a little shock. This seems to be the same thing, but it's not friction of your soles with the ground that causes the tribocharging, but it's friction of the liquid with the nozzle material. Yeah, and so this is liquid tribocharging, which is actually somewhat less understood even than normal tribocharging. Normal tribocharging is also a mess. But it's also a mess, normal tribocharging, because there's always roughness of surfaces, etc. And so maybe by looking at liquid tribocharging, we can understand this a little bit better. This is spectacular. This is a lamp that burns, but this is even more spectacular. This is actually a lightning that we can create in the lab by charging a capacitor. And you can see that we actually have a nice still image of the jet from the lightning, and this is how high-speed imaging used to work a long time ago. And so this is very important for us because I just showed you that due to coalescence we are unable to get a very nice drop size distribution because downstream it still is a broad drop size distribution, and so we are very interested to try and charge the drops because if they're charged enough they will actually repel each other and they will not coalesce. And so this actually works. So if you look very carefully, so this is a spray that is very charged because it's completely demineralized water, and you can see that due to the fact that the droplets repel each other, the droplets actually even travel back. Whereas this is the exact same spray, but with just a pinch of salt added, and the pinch of salt actually attenuates the charging by so much that we don't have a lot of charging, and so we don't get this nice cloud of monodispersed droplets. Yeah, this is much more white because it's actually much larger droplets because of all the coalescence processes. And so this incidentally solves our problem. So I started out by showing you a no spray. And so this is a little bit better than what I showed you in the beginning because the drops are much smaller, so they can travel much further into the nasal cavity. But if we do the exact same thing with the charge spray, you can actually finally see the whole nasal cavity because we added a little fluorescent dye to the spray. Yeah, so this at least solves this problem. We would of course like to understand how this works. One way of thinking about it is the nozzle wall has some charge. The water has protons and OH minus ions in it. And so if the nozzle wall is charged negatively, protons will be preferentially near the wall. Yeah, and then if you have some kind of boundary layer that drags the fluid with it, it will drag more negative ions than positive ions because the positive ions are closer to the wall where the velocity is smaller. And so you will get a net charge of your spray. We can build a little theory on that. And again, Stefan did 1,000,000 experiments because that's what Stefan does. This is the current that we measure. Yeah, so instead of having a lamp, we just put an amp meter, a nano amp meter, in the circuit. And this is a combination of the velocity, the dielectric constant. This is the thickness of this boundary layer that I just explained to you. And this is a thing called the zeta potential, which in colloid chemistry is basically a measure for the amount of charge at the surface. This collapses all the data. So that's really very nice. But we use this as an adjustable parameter. Yeah, and so we don't really understand what that parameter means because the values that we get are actually pretty high compared to what we know from colloid chemistry.
Here the zeta parameter is adjusted for each set of
Yeah.
experiments?
Yeah, so these are different liquids. So these are all the same nozzle. But these are different liquids. And so water always has the same zeta potential. You would hope, and that works out. But so ethanol, for instance, has the opposite sign of the zeta potential, and that is something that we really don't understand. Yeah. So if you think that the nozzle material is negatively charged when in water, why would it be positively charged in ethanol? Yeah. So it's an adjustable, for the moment it's an adjustable parameter. And it gets worse, because if we do different liquids, so water, acetone, nitrile, acetone, DMSO, ethanol, methanol, we get values for the zeta potential that we really don't understand. Yeah, so water charges up very nicely, and you can imagine with the little drawing that I made that might work. But DMSO charges up 3 times as much, and we have no clue why that is. Yeah, and so that brings me to the conclusion that we actually don't understand what's going on, and this is a very old problem. because there's something called the Galvani-Volta controversy, where Alessandro Volta from the charging tried to explain batteries using just physical charging mechanisms. And Galvani actually said, no, this is chemistry. Yeah, and I think part of what we're seeing here is physics, and the other part is chemistry. And it's up to us to now try and decide who is who and what is what, and how can we actually explain these zeta potentials that we now use as an adjustable parameter. And so I'll end there, thanking you for your attention. If you're interested, there's a couple of papers that are out and a couple of papers that are coming out. Thank you.
Solids. So I would like to come back to your first question, actually to your answer. So if I understand, not only you show that the effective perturbation is molecular, but also that other perturbations do not matter.
Yes.
And so can you expand on this? How could also the fitting or the extrapolation was done? Yes, can we come back to the plot?
This one. Right?
Yes, well, yes. I mean, those are, yes.
Or you mean this one? Well, so
on the x-axis, that's the time.
Yeah. And this is just what we see the little cylinder breaking up in little sausages, and we measure the amplitude of the sausage, basically, of the.
Yeah, and so how do you somehow make sense of the fact that these perturbations do not cross or interact on the upper length scales between 10 to the minus 11 to the size of the nozzle or the imperfection of the nozzle? That do
well, so I think my view on this is that Rayleigh already did this, because there is a specific wavelength that is amplified, or a specific band of wavelength that is amplified, and the rest is not. It's attenuated. And so if you go to too large or too small wave vector, the amplification is actually 0 or even negative. Yeah, and so the magic of the capillary waves is that they happen at all length scales. Yeah, so there's a dispersion relation for the relation between the frequency and the wave vector of these waves, and so the Rayleigh instability only picks up the most unstable wavelength, basically.
And you mentioned that something similar happens in solids as well.
So the title of Stefan's thesis was Fragmentation of Fluids and Solids. And we were very naively thinking that there should be some analogy between the two processes. We concluded that both processes were very different. There's a recent PRL of Emmanuel Villermoz who claims that it's somehow the same, but I haven't been able to digest why he actually thinks that. Yeah, I think it has something to do with the fact that coalescence and fragmentation can be viewed, if they're random, as leading to the same size distribution. But I think in solids, it's much more difficult, because you either get just an exponential distribution, or if you have a stressed solid, you get a power law distribution of the fragments, unless you have a stressed solid like a Duralex glass, then you get an exponential distribution.
Thank you.
Thank you very much. I think you mentioned a possible feedback mechanism for the breakup of short jets. And can you elaborate a bit on this? Is it, in your opinion, an acoustic or hydrodynamic feedback?
I think it's hydrodynamic. So what we see in experiments and in very clumsy early basilisk simulations is we really see the drop snapping off. Yeah. So if you look at drop snap off, there's a lot of energy still in these modes. Yeah. And so what we seem to see is that the snap off actually leads to a visible wave on the jet surface that can attain the origin again. Whether that is the cause of the breakup is another matter, but at least it seems to have something to do with the dripping to jetting transition. To be continued.
Thanks a lot for the talk. You mentioned that in the experiments for the thermal capillary waves, you were not able to change the temperature in the experiments. So can you elaborate on that? Why is that?
Well, so we live at 293 K, and to have a sizable effect on the on KT, I would like to go to a couple of KTs. So there are, I think, old experiments where people make liquid helium jets, but I haven't been able to find experiments where I could quantify the jet length.
So it's because of how it scales with temperature, and you don't have a range that is big enough.
Exactly.
Thank you.
Thank you very much, Daniel. So you mentioned this issue of the gamma distribution, which is something that I have some passion for. So maybe you can go back to the gamma or the Frashburg or somewhere in between. So I have no contention with everything that you have said, but I wanted to notice that one of the important things in these experiments is the range between the peak, say, and more or less the maximum. So here you have a factor of 3. If you go back, you will see the other distributions. Can you go back to the previous slides where you had other data? Maybe not this one. Maybe, I don't know. Maybe, yeah, no. Yes, this one. So for example, here you have another range, okay, from maybe 1 to 3. It's always a really thin range. But where you expect scaling is at large values of this. So you expect scaling after you had many coalescence events,
yes,
so that they can maybe converge to a uniform distribution.
So Stefan painstakingly measured 150,000 droplets. If you're telling us to do an order of magnitude better, I think Stefan will run away.
That is fantastic. So that was my comment. Okay, I have a little bit of another comment is that this is a probability for D, which is the diameter of the drop. That the Frashburg was for M, which
yes,
is the mass, so
yes,
it's D cubed. So that also introduces important differences.
Yeah.
So, but this we can discuss in private because it will bore everybody if we go into the technical details.
Yes.
D and M.
Well, so this is a factor of 3 then to the power 3, right? So it's much better.
And which is also something to take into account.
Yes.
Any other question? Stefan, sorry.
Thank you very much, Daniel. I have a question on your your effective surface tension for the spray angle. So here you assume that it's Kelvin-Helmholtz controlled by surface tension, which gives you the threshold that you wrote. But why do you assume it's only inertia and surface tension? I mean, viscosity, of course, could play a role. And then could you have the same argument with rather than an effective surface tension, you could have an effective viscosity of the interacting spray?
Well, so if I open Chandrasekhar, I get an expression for delta U as a function of the surface tension and the density difference, not as a function of the viscosity.
Sure.
don't take into account the viscosity.
Right.
Of course, Kelvin-Helmholtz is for inviscid fluids, so if you want to extend it, it's natural to say it's inviscid plus surface tension, for example. But then, of course, if you go to viscous modes, then you have the whole story about how viscous mode affect that.
Yeah, but then
it would give you another prediction. So I'm not sure.
I'm not sure either. But I think going from an effective surface tension to an effective viscosity is maybe not very helpful. Yeah, so I think somebody should just do a simulation and see whether this can be reproduced.
Okay, thank you.
Thank you. Just a quick one. Just before the slide where you compare with the gamma function, gamma distribution, why do you have, so everything collapses on the diameter except for a peak that is shifted?
Yeah, so the prediction of Freckenburg is that these distributions are self-similar. Yeah, meaning that if you rescale with the average diameter, which is what I did. Let me see.
Yeah, this one.
That they should all collapse.
Yeah, but you have a peak in the middle that doesn't.
Oh yeah, but that's because we start out with roughly monodispersed drop size distribution. Yeah, and so it's only after there's enough coalescence effects that the initial drop size and the twice the drop size and 3 times the drop size, you don't see them anymore. Okay. Yeah, that's what you see here. Yeah, the further you go from the nozzle, the smoother the distribution becomes and the smaller these peaks.
Thanks.
I think we should thank Daniel again.